Have you ever stopped to think if the tiny invisible particles that make up, well, everything, play by the exact same cosmic rule book as those giant mind-bending black holes out there?
It's a really fundamental question, isn't it?
Yeah, it's kind of a reality check.
It absolutely is. And that question hits right at the core of this huge puzzle in physics. It's this, well, head-scratching incompatibility between quantum mechanics, that's the physics of the super small n,
Right, tiny things.
and Einstein's general relativity, his theory of gravity, and the very large, the cosmos.
Okay, so black holes, the Big Bang, these are the heavy hitters, right? The really extreme zones of the universe.
Exactly.
And our guide for today, Brian Greene's The Elegant Universe, points out that these are precisely the places where both quantum mechanics and general relativity should be, calling the shots.
Precisely. Think about it. In the incredible density of a black hole's singularity, or the universe, in its first tiny fraction of a second, you've got immense mass crammed into unbelievably tiny spaces.
So you need both theories.
To truly understand what's going on there, yeah, we need both our theories on deck. You can't just pick one.
But here's where things get. Well, let's just say they don't get along so well.
Huh, that's putting it mildly.
When physicists try to mix the mathematical ingredients of these two, wildly successful theories to describe these extreme cosmic kitchens, what happens? What kind of recipe do they end up with?
Utter nonsense, basically. We're talking equations that spit out infinity, probabilities that just don't add up. It's complete breakdown. It really strongly suggests a fundamental disconnect in our understanding, right at the most basic level.
So is the universe fundamentally two-faced? Like little things follow one set of laws, big things another, and they just never the twain shall meet. That feels kind of wrong, doesn't it?
It does feel wrong.
Like a magician with two completely different sets of instructions for the same trick.
That's the central mystery we're digging into. Can reality truly be this divided? This friction, this hostility between quantum mechanics and general relativity, it hints that there's a deeper, more unified story waiting to be told.
And, this isn't the first time Einstein had to play peacemaker in a physics argument, is it? Or source material mentions a previous dust-up involving his special relativity.
That's a really good point. Actually, the arrival of special relativity with its famous rule that nothing can travel faster than light, that actually threw a big wrench into Newton's long-standing theory of gravity.
Ah, Newton. His idea was that gravity was this instantaneous connection, right, across the whole cosmos. Like the sun just knows where Earth is and tugs on it instantly.
Exactly, like pulling an invisible string, right here, right now. Newton's theory, for all its amazing successes explaining orbits, falling apples, all that it described gravity as an influence that traveled infinitely fast.
But then Einstein's special relativity comes along and says,
Hold on a minute. Cosmic speed limit in effect. Nothing goes faster than light. That's a clear conflict. You can't have both.
so Einstein, the ultimate physics ref, steps into the ring in 1915 with his general theory of relativity and somehow resolves it. How did he manage that?
He did, and it was a total game changer. I mean, really revolutionary. Einstein reimagined gravity not as a force in the traditional sense, like a pull, but as a consequence of space and time themselves being warped and curved.
Warped and curved by what?
By the presence of matter and energy, these bends and curves in the fabric of space-time, that's what transmits gravity.
Whoa, okay, so it's not the sun yanking on Earth with some invisible rope.
Yeah.
It's the sun's mass actually bending the space around it, and Earth is just rolling along the curves in that cosmic dip.
You got it. Space and time aren't just an empty stage anymore. They become active participants in the whole cosmic play.
They're not just inert bystanders.
No. They respond to matter and energy, and that response is gravity. And this brilliant idea resolved the conflict with special relativity because these gravitational influences, these warps, they now propagate at the speed of light, the speed at which space-time itself can ripple.
Okay, so one conflict down. But To really wrap our heads around why quantum mechanics and general relativity are still sparring partners, we need to zoom way, way in, don't we? To the tiniest bits of the universe.
That's right. We need to look at the building blocks. Think back to the ancient Greeks and their idea of atoms, these supposedly indivisible, uncuttable units. It was an incredible idea for its time.
Yeah, really ahead of its time.
And while our understanding of what's truly fundamental has evolved massively, that core idea of a few basic building blocks creating everything, that stuck around.
From the uncuttable atom to, well, the very much cuttable atom, as it turned out. We learned about the nucleus, right? With protons and neutrons inside and the electrons whizzing around.
The little solar system model.
And then physicists basically started playing demolition derby with these atoms.
Yeah, exactly. Using increasingly powerful particle accelerators, physicists have been smashing matter together at incredibly high energies. They're essentially trying to recreate conditions from the very early universe, just after the Big Bang.
And the debris they found when they smashed things up,
Yeah.
well, it was more than they expected, wasn't it?
Oh, yeah. It was a whole cosmic zoo of fundamental particles. More quarks popped out with these wonderfully weird names. Charm, strange, bottom, top.
Charm and strange, I love those.
Right. And heavier, more energetic cousins of the electron called muons and tauus. And these almost ghost-like particles, the neutrinos, electron, muon, and tau neutrinos.
It's like the universe has a far more complex ingredient list than we first thought. Like way more complex.
Definitely. And the complexity doesn't even end there. For every single one of these particles, there's a corresponding antiparticle.
Antiparticle. Like an evil twin.
Sort of. Same mass, but with opposite electrical charge and some other quantum properties flipped. And when matter and antimatter meet...
Kaboom. Annihilation. Right.
Yeah.
They just wipe each other out in a burst of pure energy. EMC squared in action.
Precisely. That's probably why we don't see much antimatter just floating around naturally today. Most of it likely met its matter match very early on in the universe's history, and poof.
Okay, so we've gone from simple, uncuttable atoms to this really intricate world of fundamental particles and their anti-twins. But where does electromagnetism fit into this picture, and how does that connect back to the speed of light?
Good question. Back to the 1800s, James Clerk Maxwell. Our sources highlight how he did something amazing. He unified electricity and magnetism.
Pulled them together under one roof, creating the electromagnetic field? That sounds like a pretty big deal even on its own.
It was a monumental achievement. Maxwell's work revealed that electricity and magnetism weren't actually separate forces at all, but just different aspects, different faces of a single underlying electromagnetic field.
Okay.
And his theory had this truly remarkable consequence. It predicted that disturbances in this field, things like radio waves or, light travel at a fixed unvarying speed.
And that speed turned out to be...
Yeah.
Don't tell me it's the speed of light.
Exactly. So light itself is just one type of electromagnetic wave, a ripple in that field. And crucially, Maxwell's theory showed that all electromagnetic waves, including visible light, are the ultimate speedsters of the universe. They never speed up, they never slow down relative to anything. Light always travels at the speed of light.
That constant speed of light. That's the linchpin for special relativity, isn't it?
It really is. It's a fundamental cornerstone for what comes next with Einstein.
Which brings us back to Einstein and his special relativity and how our everyday intuition about motion and time can really, really lead us astray when we start dealing with things moving close to light speed.
Oh, absolutely. Our intuition is built on low-speed experiences.
Our sources use that great example. You're in a car, the trees outside look like they're moving backwards.
Right.
But for a hitchhiker standing still by the road, the trees are obviously stationary.
It's a perfect illustration of the relativity of motion. What one person sees as still, another sees as moving, all depending on their own motion. Basic stuff.
But special relativity takes this idea and runs with it into some truly mind-bending territory, especially when things get really fast.
Yeah, near light speed, things get weird.
Remember that hypothetical drag race? Slim in his super fast Trans Am hitting, what, 120 miles per hour?
Uh-huh.
Before Einstein, we just assumed that Slim in the car and Jim watching from the sidelines, their stopwatches, would show the exact same time for the race, right?
Absolutely. That's our ingrained common sense understanding. Time is time. Clocks tick the same everywhere.
But according to special relativity,
Jim on the sideline would actually measure a slightly longer time interval than Slim in the moving car. It's a tiny, tiny difference at 120 mile per hour, practically imperceptible, but according to the physics, it's real.
and they'd also disagree slightly on how long the car is.
Yep, length contraction too.
Yeah.
Again, minuscule at normal speeds, but fundamentally there.
So measurements of time and even length aren't these fixed universal constants. They actually change depending on how the observer is moving relative to what's being measured. That's pretty wild.
It is wild, and we just don't notice it in our daily lives because we're all moving so incredibly slowly compared to the speed of light. These relativistic effects only become really obvious at significant fractions of c.
Okay, but then there's this even more bizarre finding. The speed of light itself. It stays the same for everyone, no matter how they're moving or how the light source is moving.
That's the really counterintuitive part.
It just completely breaks our normal understanding of how speeds add up or subtract.
It does. Think about throwing a ball while you're running. If you throw it forward, its speed relative to someone standing still is your running speed plus the speed you threw the ball at, right?
Right, simple addition.
But light doesn't play by those rules. If you shine a flashlight while you're running really fast towards someone, they don't measure the light beam hitting them any faster than if you were just standing perfectly still shining the flashlight.
It's like that analogy in the book about the hand grenade versus the beam of light. If someone throws a grenade at you, running away makes it hit you slower.
Right, it reduces the relative impact speed.
But if they threw a beam of light at you, running away wouldn't change its speed relative to you one bit. It still zips past you at sea.
Exactly. It's mind-boggling, but experimentally verified again and again. This absolute constancy of the speed of light has some very strange consequences. One of the most famous is time dilation.
Time dilation, that's the idea that time slows down for moving objects, right?
Relative to a stationary observer, yes.
The light clock thought experiment is such a neat way to visualize this. You've got two mirrors facing each other.
Parallel mirrors.
And a single photon, a particle of light, just bouncing back and forth between them. Each round trip, say, is one tick of this clock.
Right, a very simple fundamental clock. Now imagine that entire light clock setup is moving past you at a very high speed, horizontally.
Okay, zooming past me.
From your stationary perspective, you see the photon inside that moving clock having to travel a longer path. It's not just going straight up and down anymore.
Ah, because the mirrors are moving sideways while the photon is in flight between them. So it has to travel on a diagonal path.
Exactly, a longer zigzag path from your point of view.
Okay.
And since we know this is the crucial bit, that the speed of light is constant for everyone, for you watching and for someone writing with the clock.
Then if the photon travels a longer path than the moving clock, but its speed is the same.
It must take more time to complete that longer path, which means more time must have elapsed for that moving clock to complete a single pick, as observed by you, the stationary observer.
So from my perspective, the moving clock is ticking slower. Time is literally running slower for the moving clock. Whoa.
That's time dilation. Time isn't this universal, steady metronome ticking the same everywhere. It's relative. It stretches, it dilates, depending on relative motion.
And that's why those fast-moving muons we mentioned earlier, the ones created high in the atmosphere, they seem to live longer than identical muons at rest in the lab.
Correct. From our perspective on Earth, their internal decay clock is slowed down because they're moving so fast, allowing them to reach the ground before decaying.
But from the muon's own perspective, its life feels perfectly normal.
Exactly. From its frame of reference, its internal clock is ticking normally. It experiences its standard lifespan. It's just that our measurement of its time has stretched relative to its own experience of time. Mind-bending stuff.
Okay, so special relativity really, really messed with our common sense notions of space and time. But Einstein wasn't done, was he? He spent like a decade wrestling with gravity after that.
That's right. Our sources mention his tormented decade. Einstein was deeply troubled by the fundamental incompatibility between his shiny new theory of special relativity and the old established theory of Newtonian gravity. Remember the infinite speed problem?
Yeah, gravity can't be instant if nothing's faster than light.
Exactly. His unwavering belief in the consistency of the universe, that it should all fit together, drove him relentlessly to find a resolution. This led him eventually to his masterpiece, general relativity.
And he was pretty sure he was right, wasn't he? There's that famous quote.
Oh, yeah, about feeling sorry for the dear Lord if the theory turned out to be wrong because the theory was correct. That's supreme confidence, born from years of intense work.
That's amazing. So we know general relativity reinterprets gravity as this warping of space-time. But how did he even get to that radical idea? What was the breakthrough? The principle of equivalence sounds important.
It was absolutely key. The principle of equivalence is quite simple on the surface, but profound in its implications. It basically states that the effects of gravity are completely indistinguishable from the effects of acceleration. You can't tell the difference locally.
Einstein used that thought experiment, right? Albert in a sealed rocket ship.
That's the classic one. Imagine Albert is in a windowless rocket, maybe floating in empty space, far from any planets or stars. If the rocket isn't firing its engines, he just floats weightlessly inside.
Okay, standard zero-G.
Now, imagine the rocket starts accelerating upwards, constantly picking up speed. What does Albert feel?
He'd feel a force pushing him down onto the floor of the rocket, wouldn't he? Like gravity.
Exactly. It would feel precisely like the pull of gravity. If he dropped a ball, it would fall to the floor. If he stood on a scale, it would show a weight. Without looking outside, there's absolutely no experiment he could do inside the rocket to tell whether he's accelerating in empty space or just sitting perfectly still on the surface of the Earth.
The effects are identical.
Huh. This indistinguishability is profound. Einstein realized, well, if acceleration can perfectly mimic gravity, then maybe gravity itself is related to acceleration in some fundamental way. Maybe gravity is a manifestation of space-time itself accelerating, or rather being curved or warped.
And that leap led to the whole curved space-time idea.
That was the crucial leap of insight. Gravity isn't a force acting through space. It's a feature of space and time itself. The presence of mass and energy tells space-time how to curve.
And the curvature of space-time tells matter how to move.
You've got it. That's the essence of general relativity.
So the classic analogy, a bowling ball on a stretched rubber sheet, the ball makes a dip, a curvature in the sheet.
Exactly. That's like a massive object, say the sun, warping the fabric of space-time around it.
And if you roll a little marble nearby,
It won't go in a straight line anymore. It'll follow the curve created by the bowling ball. Just like the Earth orbits the sun, it's not being mysteriously pulled by a force, it's just following the natural, straightest possible path, called a geodesic, through the curved space-time created by the sun's mass.
wow. So the warping is gravity. It's not causing gravity, it is gravity.
In Einstein's view, yes. It replaced Newton's mysterious action at a distance with a local mechanism, the geometry of space-time.
And this warping isn't just about space, is it? Gravity messes with time too, according to general relativity.
Absolutely. Gravity distorts time as well as space. The stronger the gravitational field, the slower time flows.
Slower. How does that work?
Our source material gives that nice example of George and Gracie near the sun. Imagine Gracie stays far away where the sun's gravity is weaker. George lowers himself down, closer to the sun's intense gravitational field.
Okay, George is getting closer to the massive object.
When they compare their clocks later, George's clock will be found to have ticked more slowly than Gracie's. Time literally ran slower for him down there in the stronger gravity.
So not only does motion affect time, special relativity, but gravity affects time too, general relativity. Time is really not absolute at all.
Not in the Newtonian sense, no. It's relative, it's flexible, it's part of this dynamic fabric of space-time that responds to mass and energy.
And general relativity wasn't just some beautiful abstract idea, right?
Yeah.
It actually made predictions that could be tested.
Hmm.
Our sources mention Mercury's weird orbit.
Yes, that was a huge early success. For decades, astronomers had known that Mercury's elliptical orbit around the sun wasn't behaving quite as Newton's theory of gravity predicted. There was this tiny extra bit of rotation, a wobble in the orbit called the perihelion precession.
And nobody could explain it properly using Newton's laws.
Right. People proposed unseen planets, dust clouds, all sorts of things. But when Einstein applied the equations of his new theory, general relativity, to Mercury's orbit,
It matched perfectly.
it nailed it. The equations naturally predicted the extra little wobble due to the way the sun's gravity warps space-time near it. This was a monumental triumph for general relativity and gave Einstein enormous confidence that he was on the right track.
Okay, and finally, this whole idea of an expanding universe, that comes out of general relativity too.
It does. The equations of general relativity, when applied to the universe as a whole, naturally suggest that the fabric of space itself isn't static. It can expand or contract. And observations by astronomers like Hubble confirm that distant galaxies are indeed moving away from us, implying space is expanding.
And if you run that movie backwards, if space is expanding now, then in the past it must have been smaller, denser, hotter.
Exactly. If you rewind the cosmic expansion far enough back in time, everything must have been compressed together into an incredibly hot, dense state. That leads directly to the concept of the Big Bang.
The universe originating from this almost unimaginably tiny, hot, dense point containing all the energy and matter that would eventually become, well, everything we see.
Yeah, that's the picture painted by combining general relativity with cosmological observations. An awe-inspiring and, as you say, slightly terrifying picture of our cosmic origins.
It really is, and it's right there, isn't it? In trying to understand that initial moment, that singularity, and also the singularity inside black holes, that the big problem resurfaces.
That's where the clash becomes unavoidable. You have immense gravity, general relativity's domain, acting on incredibly small scales, quantum mechanics domain. You need both theories.
And they just refuse to cooperate.
They give nonsensical answers. Infinities pop up. The math breaks down.
So we've circled back. We saw how Einstein brilliantly resolved one major conflict in physics, Newton versus special relativity, with his general theory of relativity. But in doing so, he kind of set the stage for this even deeper, more perplexing conflict with quantum mechanics.
That's a great way to put it. The universe seems to operate by these two incredibly successful yet fundamentally contradictory sets of rules. One for the large, one for the small.
General relativity gave us this radical new vision of gravity as warped space-time, dynamic and interconnected. But when we try to apply that beautiful picture down in the quantum realm, the world of particles and uncertainty, it just doesn't fit.
The frameworks are incompatible as they stand.
Which leaves us with this huge, tantalizing question hanging in the air. Is there a single, maybe even elegant, underlying framework out there that can somehow unite these two pillars? A theory of everything.
That's the holy grail of modern fundamental physics, finding that unified theory.
It's a pretty mind-blowing prospect, isn't it? Like finding the master instruction manual for reality itself.
It is. And as we continue this deep dive in future discussions, we can start to explore some of the most promising and, frankly, some pretty wild ideas like string theory that attempt to bridge this gap.
Ideas that might force us to rethink everything again, maybe even how many dimensions there really are.
Potentially, yes. The search for unification often leads to radical new perspectives on space, time, and reality itself. It certainly gives you a lot to chew on.